let's introduce the idea of time value of money payments. So far what we've been looking at is future value, present value, interest, and end, but payments really haven't played in. Before we get into payments, we need to understand cash flows in the world of time value of money. So forget what you know about positives and negatives and algebra. Just reset that mind frame for time value of money. Whenever we have a cash flow going into a wallet, a positive cash flow, whenever we add money to a cash account, whenever we make a deposit in our cash account, that's going to be a positive cash flow going into our wallet. So in time value money problems, if we liquidate an account, it goes in our wallet, that would be a positive cash flow. Generally speaking, future value is usually positive in these time value money problems. Negative cash flows trip people up a little bit. But a negative cash flow is whenever money leaves your wallet. So conceptualize a wallet and think money going out of it. Well, when does money leave your wallet? Well, when you make a withdrawal, when you save towards a goal, when you pay a bill, any of these things, money leaves your wallet, right? Cash is leaving. That's a negative cash flow. And we've got to get positive and negative cash flows right for anything around payments to start making sense algebraically or in Excel. So let's visualize payments for a minute, okay? Payments are going in, they're going out, they're flying all over the place. But again, we take the present value, we grow it at an interest rate, and payments impact that cash flow. They can add, right? I can add to the cash flow. I can pull out of that cash flow. But there's an interesting thing around payments, and that is the timing of when a payment occurs. I can have a payment start at the beginning of my timeline, at the start of my problem, at time period 0. I can say, hey, we're going to go ahead and put money in, pull money out, the beginning of a period. So anytime we have expenses or cash in advance, like pay for a year of school or pay for a year of retirement, we normally have a beginning period cash flow. We call any beginning period cash flows annuity due. It is an annuity due payment. Those are the words we use to describe cash flows at the beginning of any period. And we're going to treat those different than cash flows at the end of a period, right? Ordinary annuity payments, we call those ordinary annuity, or any sort of payment stream that starts at the end of a cash flow. An easy way to remember what those are is Major League Baseball, mortgages, loans, and bonds. Those cash flows always occur at the end of a cash flow, right? We borrow the money, we buy the house, a month goes by, we make our first mortgage payment, right? We buy a bond, 6 months goes by, we get a coupon. Ordinary annuity, Major League Baseball. So things that happen at the end of a period, we always use an ordinary annuity payment. You might be thinking, Craig, is there a difference here? All right, well, let's take a look and do a couple of illustrations. First up, we need to label payments. We always label the payment today at the start of any problem as time period 0. You'll see up at a 0 there. Then you've got end of periods 1, 2, 3, 4, and 5. And so for this timeline, it's a 5-year timeline, and you can see where we start at 0, and then we have end of period 1, so forth and so on, until end of period 5, which is the end of our problem. And so let's see how they're different. I want to start with an annuity due. Now let's say I'm going to go ahead and invest $500. You'll see it's negative, right? It's leaving my wallet. I'm going to invest $500, $500, $500, $500, and $500. I'll make 5 $100 investments on my timeline. I'm going to start today. So what's it worth? Well, it's actually pretty easy. We're just going to take the sum of each payment's future value. Now, I know it seems time intensive, and I'll save you steps later, but for now in learning, we would take the future value of the first payment. Well, how many years does it have to compound? 1, 2, 3, 4, 5, right? We can count on our timeline. And the second payment only has 4 years to compound, and then 3, and then 2, and then 1 respectively. So if you take the sum of those payments, you're left with this. The future value of the first payment's $805, then we go $732, $665, $605, $550. And if you're looking at this slide, the sum of all those payments, assuming a 10% return could be earned, was $3,357.81. That was the sum of those cash flows. That's the future value we would expect for the problem. All right, a little time intensive, but fairly straightforward. Now, if we want to solve our annuity due using some algebra, instead of using that timeline example, well, here's the formula for you. Go nuts. We take the payment amount of $500 and then we find our annuitization factor. And that annuitization factor in this case is a little tricky. We take 1 plus the interest rate raised to the nth power, subtract 1, multiply that times 1 plus the interest rate. We divide all that by the interest rate. And needless to say, at this point in the game, we get an annuitization factor of about 6.715. And so if you take the $500 payment times the annuitization factor, you get $3,357.81. Now I think it's a little easier to see on our timeline, right? But it's the same math. It gets you to the same end, but instead of doing 5 problems and adding them up, you just have to do 1 problem to find the answer, okay? Now that's annuity due, right? But annuity due doesn't happen all the time. We very well could have seen an ordinary annuity. And what's different? Well, the first big difference in an ordinary annuity is that we look at this world and we start at 0 instead of starting with a payment. So now we're going to say 0, 5, 5, 5, 5, 5. And the big difference mathematically is this very first payment only compounds 4 times instead of 5. So we lose 1 compounding cycle on 1 payment. What does that look like? Well, mathematically, it's actually quite a bit easier to do an ordinary annuity. We need to find an annuity factor, but there's a little less to find it. We take 1 plus I, raise it to the n, subtract 1, divide it by I, and that gives us the annuity factor we would apply against the payments. So with ordinary annuity on this slide, you'll see that we take 500 times the new annuity factor, 6.1051. We get 3,052 and some change. Why do we care? You may be going, come on, Craig, what's the difference here? Well, I'll tell you exactly what the difference is. To find an ordinary annuity and how it relates to an annuity due, it's pretty straightforward. If our ordinary annuity answer was 3,053, what is that? Well, that's the annuity due divided by 1 plus the interest rate. And you could flip the same around. The annuity due is equal to the ordinary annuity times 1 plus the interest rate. That 1 extra period of compounding is the difference in those numbers. Our annuity due, 3358. That's equal to 3053 times 1 plus the interest rate. And that's how annuity due and ordinary annuity play together in the sandbox. I can make it harder if we want to. We can add a present value and kind of show you the same thing. So with this example, I have a present value of 9,000 and payments of 500. So how would this look? Well, I put 9,000 in the account and then I do 5 $500 payments. You can see 95, 5, 5, 5, 5. So on a timeline, this is what that looks like, right? We can compound that 9,500, turns into 15,000, and then we compound the 5, the 5, the 5, and the 5, and we can get our answer of 17,852 if we do it longhand and we compound each of the 5, okay? Now, just some rules on annuity payments. They may or may not be even. In everything we've done so far, they're pretty even. They don't have to be. I can use uneven cash flows, and we'll teach you how to do that a little later. I can compound or discount annuity payments. I can put them forward in the future. I can just as easily discount them back in time. Excel's a pretty easy way to solve payments, but we have to be careful with positives and negatives or it will sink us. When is a cash flow positive? When is a cash flow negative? And with annuity payments, we don't need to solve everything in annual states. So we can use monthly interest, weekly interest, daily interest, because we're not really comparing apples and apples right now. We're usually just solving, looking at one annuity problem at a time. Now that we've looked at cash flows, positive and negative, and ordinary annuities and annuity dues, let's go ahead and give it a shot. So if you have 4 items, you can always find the 5th, and in this case, we're going to find a payment on an annuity. So let's see what we're trying to do here. You just financed a $300,000 fixed-term 30-year mortgage at 6.25%. What are your monthly payments? All right, before we can do anything, we need to find a monthly interest rate to use here. So what we're going to do is we're going to take that 6.25% annual and divide by 12, right? A monthly mortgage is going to accrue interest, right, once a month at the end of the month. So we take that 0.0625 divided by 12, you get 0.005208, And that's going to be our monthly interest rate. So now we can actually move forward and have a little fun. 360 months, each month is accruing at 0.00528. 300,000 is present value. So how do I go ahead and solve the annuity? Well, I can use that annuitization factor, right? Annuitization factor. And so if I really want to do this longhand, we would say present value equals the payment times 1 minus 1 plus the interest rate raised to the nth power divided by I. Now that is a bit tricky. I'll be the first to say we'll probably use Excel here. But you can go through the steps and you can find that the payment longhand came out to $18.63 and 96 cents. I rounded up to $18.64. All right, so there's your equation answer, and the first time we can really use an annuity factor, but we had to understand here that we're going to have, in this case, a negative payment, right? It's going to be applying towards the principal. It's going to be paying it down, so cash flow will leave our wallet to that end. If you're looking at it on a timeline, pretty straightforward. You've got 360 months, 0 FV, 6.25 is I, and 1864 was the payment. Now we're going to pivot over to Excel. I'm going to show you how to do it there. But Excel probably where we're going to start doing payments. We probably won't do them algebraically, but it will definitely get us moving, and we'll see how all that plays together. Let's take a look at Excel to answer the problem from our last module. What we're going to do this time is we take a look at present value, where present value of the loan we borrowed is $300,000. So go ahead and key that in your Excel spreadsheet. Now it's positive, remember, because we took the money from the bank, so it went into our cash flow. Basically, we took that $300,000 and we got to pay it back. So present value is positive 300. We know it's 360 periods, right? Those things are pretty straightforward. The problem we're into is the rate. So what I've done is I've just taken an annual rate, and we know that the rate will accrue monthly, right? This is a monthly calculation, so no need for an effective rate. So we're going to take 6.25%, divide it by 12 months a year. That's what's dumping over in the rate column, and you get 0.005208. All right, we go ahead and then let Excel do the heavy lifting. We know that this is an ordinary annuity, Major League Baseball, mortgages, loans, bonds, ordinary annuity. Make sure that that's a 0. And then go ahead in your payment, right? You just hit equal payment, and you can see Excel asks you for the rate, number of periods, present value, future value, and type, and I've got all that keyed in a little spreadsheet here. So the payment, $1847.15. In my opinion, a little easier than doing it by hand, but that's going to be what the monthly mortgage payment is for this problem.